this lesson, you will learn about the types of electric circuits and examine how a closed electric circuit works. At the end of this lesson, you will be able to illustrate the working of an electric circuit, identify the significance of circuit diagram, define the types of electric circuits, calculate the equivalent resistance in series circuits, and calculate the equivalent resistance in parallel circuits. The electric current in a circuit is due to a potential difference between two terminals of the battery. To illustrate the concept of potential difference and the nature of an electric circuit, consider two metal plates positioned parallel to each other. Each of these plates carries an opposite charge, one positive and the other negative. This arrangement of charged plates creates an electric field in the region between the plates. This field is directed away from the positive plate and towards the negative plate. A negative charge from the negatively charged plate moves towards the positive plate. This occurs without the need of energy in the form of work. It occurs naturally and thus lowers the potential energy of the charge. In the given arrangement, the positive plate is at higher potential and the negative plate is at lower potential. Thus, there is a difference in electric potential between the two locations. Now let's connect these plates using a metal wire. On connecting these plates, the wire serves as a sort of pipe for the flow of charge. Gradually, negative charges move from the negative plate through the charge pipe to the positive plate. As a negative charge leaves the lower plate, the plate becomes less negatively charged. Similarly, as a negative charge reaches the positive plate, the plate becomes less positively charged. The amount of positive and negative charge on the two plates slowly diminishes. Eventually, the electric field between the plates becomes so small that there is no observable motion of charge between the two plates. The plates ultimately lose their charge and reach the same electric potential. In the absence of an electric potential difference, there will be no charge flow. This illustration demonstrates the working of an electric circuit. For a true circuit, charge must flow continuously through a complete loop, returning to its original position and cycling through again. The necessity for a complete loop in a circuit can be demonstrated through an example. If you take a battery pack, that is, a collection of cells, a light bulb and some connecting wires, and make a circuit, the bulb lights up. However, when you disconnect the wires, the bulb does not light up. The fact that the bulb lights up and remains lit when the wires are connected is evidence that charge is flowing through the bulb's filament and that an electric current has been established. A closed loop through which charge can continuously move is referred to as a closed circuit. If the loop is not complete, then charge stops flowing, and such a circuit is known as an open circuit. Also, for continuous flow of charge, there should be an electric potential difference across the two ends of the circuit. This potential difference is usually maintained by the use of a cell or a battery. Constructing an electric circuit can be a complex task, as a circuit uses various kinds of electrical components. A diagram is drawn to represent the components and flow in a schematic form. This schematic representation of various electrical components using suitable symbols is called a circuit diagram. Circuits that consist of just one battery and one load resistance are very simple to analyze, but they are usually not found in practical applications. Most often, you find circuits with more than two components. You can connect the components in a circuit in two ways: in series and in parallel. Let us first examine a series circuit. In a series circuit, each device is connected such that there is only one pathway through which current can traverse the external circuit. Each charge traversing the loop of the external circuit passes through each resistor consecutively. In a parallel circuit, each resistor is placed in its own separate branch. The presence of branch lines provides multiple pathways for a current to traverse the external circuit. On arriving at the branching location or node, a charge selects the branch on which it will travel back to the low potential terminal. Thus, each charge passing through the loop of the external circuit passes through a single branch. Consider the series circuit shown in the figure. Since there is only one pathway through the circuit, every charge encounters the resistance of every device. Therefore, adding more devices results in a larger overall or net resistance. This increased resistance serves to reduce the rate at which charge flows. That is, it serves to reduce the electric current. The rate at which charge flows through the external circuit is the same all through. The amount of current varies inversely with the amount of overall resistance. There is a clear relationship between the resistance of the individual resistors and the overall resistance of the circuit. As far as the battery supplying the charge is concerned, the presence of three resistors R1, R2 and R3 in series is equivalent to having a single resistance equal to R1 plus R2 plus R3 in the circuit. The equivalent resistance of a circuit is the amount of resistance that a single resistor would need in order to equal the overall effect of the collection of resistors in the circuit. For series circuits, the mathematical formula for computing the equivalent resistance R equivalent is equal to R1 plus R2 plus R3. The current in a series circuit is equal at all points. Charge does not pile up and begin to accumulate at any given location. Therefore, the current at one location is never more than that at other locations. Similarly, charge is not used by resistors. Therefore, the current at one location is never less than that at other locations. Thus, charges can be thought of as marching together through the wires of an electric circuit, all at the same rate. The amount of current flowing through the circuit is the same at all points. The current in the first resistor is equal to the current in the last resistor and the current in the battery. That is, the total current passing through a circuit is equal to the current at any point in the circuit. Mathematically, you can write I total is equal to I1 is equal to I2 is equal to I3. You can calculate the current if the battery voltage and the resistance of individual resistors are known. Using the individual resistor values and the equation above, you can compute the equivalent resistance. Additionally, using Ohm's law, the current in the battery and thus through every resistor can be determined by finding the ratio of the battery voltage and the equivalent resistance. That is, I battery is equal to I1 is equal to I2 is equal to I3 is equal to V battery divided by R equivalent. In a series circuit, the battery supplies energy to the charge to move it through the cells and to establish an electric potential difference across the two ends of the external circuit. As the charge moves through the external circuit, it encounters a loss of electric potential. This loss in electric potential is referred to as voltage drop. If an electric circuit powered by a battery V is equipped with more than one resistor in series, then the cumulative loss of electric potential is V volts. Thus, there is a voltage drop for each resistor, but the sum of these voltage drops is V volts. The same as the voltage rating of the battery. The total voltage drop of the circuit can be expressed mathematically as V is equal to V1 plus V2 plus V3, where each voltage drop is equal to the product of the total current in the circuit and the resistance in the respective resistor. Substituting the values of individual voltage drops in this expression, you get IR is equal to IR1 plus IR2 plus IR3. By solving this expression, you get the equivalent resistance of cells is series circuits, R, as the sum of resistances of each resistor in the circuit. Hence, R is equal to R1 plus R2 plus R3. In a parallel circuit, there are multiple pathways by which current can flow. If you add another resistor in a separate branch, it provides another pathway for the charge to flow. Therefore, when more resistors are added to a parallel circuit, the overall resistance decreases. This decreased resistance increases the current. This phenomenon can be explained using the example of tollways. A toll booth provides resistance to car flow on a tollway. Adding more toll booths in a toll station will provide more pathways for cars to drive through. These additional toll booths will decrease the overall resistance to car flow and increase the rate at which they go through. Similarly, in a parallel circuit, charges divide up into separate branches. Based on the resistor in each branch, the current across branches can vary. Nonetheless, when taken as a whole, the total amount of current in all the branches is equal to the amount of current at locations outside the branches. Thus, the amount of current in the circuit is the same across all points outside the branches. However, it is split over multiple pathways. This principle can be represented as I total is equal to I1 plus I2 plus I3, where I total is the total amount of current outside the branches and in the battery, and I1, I2 and I3 represent the current in the individual branches in the circuit. In a parallel circuit, a charge does not pass through every resistor. Rather, it passes through a single resistor. Thus, the entire voltage drop across that resistor must match the battery voltage. It doesn't matter whether a charge passes through resistor 1, resistor 2 or resistor 3. The voltage drop across that resistor must equal the voltage of the battery. Put in equation form, this principle is expressed as V is equal to V1 is equal to V2 is equal to V3. Let the equivalent resistance be R. As you saw earlier in series circuits, you can calculate the amount of current flowing through each resistor as the ratio of the voltage drop across that resistor to the resistance of that resistor. Substituting the values of I1, I2 and I3 in I total is equal to I1 plus I2 plus I3, you get V divided by R is equal to V divided by R1 plus V divided by R2 plus V divided by R3. This gives you 1 divided by R is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. Looks like the connection is important for Chamku to glow, doesn't it?
In this lesson, you will learn to connect the components of an electric circuit. At the end of this lesson, you will be able to create an electric circuit by connecting an electric cell to a bulb and make a switch for an electric circuit.
You're right. Chamku stops glowing as soon as his connection with cello is broken.
A bulb should be connected to an electric cell for it to glow.
Here, I have another torch bulb and a new cell. How should I connect them to make the bulb glow?
Let me show you. We will also need 4 pieces of wire and an adhesive tape.
There you go.
Let's start off. First, from the ends of all the 4 wires, remove the plastic covering such that a small length of the metal wire is exposed. Fix the exposed end of a wire to the positive terminal.
Cool. What about the negative terminal?
Fix the exposed end of another wire to the negative terminal of the cell. Now, fix the exposed ends of the other 2 pieces of the wires to the 2 terminals of a bulb with adhesive tape. This is what the bulb and the electric cell will look like with the wires attached to them.
Okay. But the bulb is not yet glowing. What do we do next?
We now connect one of the wires of the bulb to a wire from the electric cell. Then, we connect the second wire from the bulb to the remaining wire from the electric cell.
Hey, look! The bulb is glowing now.
Yes, it is.
What happens if we connect the wires from the bulb to the same terminal of the cell?
Why don't we try it and find out? See? Can you see the bulb glowing now?
No, it's not glowing.
Let's try connecting it in another way. Does the bulb glow now? What's the result?
It's still not glowing.
Want to try one more way?
Sure. Let's connect all the wires to the positive terminal now. The bulb still doesn't glow. I guess that the connection should be made in a specific way.
Right. Now, let's reconnect it the way I showed you the first time.
Yes, the bulb is glowing now.
Right. Electricity needs a path to pass from the positive terminal to the negative terminal of the cell. When the positive and the negative terminals of an electric cell are connected to the 2 terminals of a bulb, the path is completed and the bulb glows. A connection that provides a complete path for the electricity to pass from the positive terminal of the cell to its negative terminal outside an electric cell is called an electrical circuit.
Hey, look! I have another bulb. Let me try making an electric circuit with this.
Sure. Go ahead.
What happened? Why doesn't the bulb glow? I connected it correctly, didn't I?
This bulb is not glowing because it is fused.
I've often heard of bulbs getting fused. What causes a fuse?
Well, one of the reasons could be a break in the filament of the bulb. When the filament is broken, there is a break in the flow of electricity through the terminals of the bulb.
Oh, you mean the circuit is broken?
You could say that. Basically, with the breaking of the filament, the path required by electricity to flow is incomplete. Hence, the bulb does not glow.
Hey, look, Flashy! I made a torch. Now I can use this when there's a power cut.
Wow! Can I see it? Cool! But how do you switch the light off on this torch?
Look here. We need to disconnect one of the wires to switch off the battery.
But then, you'll need to reconnect the wire manually to get the bulb to glow. Right?
Yes, of course.
Look at what I have here. This is a switch. You can use this to make it easy to switch the bulb on and off.
How does a switch do that?
A switch is a device that is used to stop the flow of electricity by breaking the circuit. A switch enables you to break or complete a circuit on the click of a button.
How can I create a switch for my torch?
Come, I'll show you. We will need a thermocol piece, a pair of thumbtacks, a metal paper clip, 4 pieces of wire, an electric cell, and a torch bulb.
There we are. What now?
We start by creating the circuit just like you did in creating your torch. There will be one difference though. We will leave one of the wires of the electric cell and the bulb unconnected. We connect one end of the loose wire from the cell to a thumbtack, which is fixed on the thermocol. Now, we connect one end of the loose wire from the bulb to another thumbtack fixed to the thermocol close to the thumbtack fixed earlier. The distance between the 2 thumbtacks should be less than the length of the paper clip. There, your switch is ready.
Oh, but how do I click it on?
When you want to switch the bulb on, just bring the paper clip in contact with the thumbtack.
Right. That will complete the circuit. I can see the bulb glowing. And to click it off, I take the clip away from the thumbtack?
Yes. Simple, isn't it? Did you know? Switches can be found in a variety of applications. A few common types of switches are toggle switch, used in our houses; push button switch, used in the starter of a water pump; joystick switch, used in the remote control unit of a toy car.
This brings us to the end of this lesson on electric circuits. In this lesson, you learn to connect an electric cell to a bulb, explain how an electric circuit works, and make a switch for an electric circuit.
We use electricity for almost all the appliances at home. Lights, fans, the television, the music system, and the computer all run on electricity. Electricity drives our world. Electricity is also known as electric current. In this lesson, you will learn about electric current, its causes and applications. At the end of this lesson, you will be able to identify the features of electric current, explain how potential difference generates electric current, define electrical resistance, identify the factors affecting resistance, and state and apply Ohm's law. Before learning about the cause and applications of electric current, let us examine the features of electric current. Typically, in a conductor, free electrons move randomly. When these electrons are influenced to move uniformly in a specific direction, we get electricity, or electric current. The direction of electric current is the same as the direction of flow of electrons. Electric current requires a continuous path of conductive material to provide a conduit for electrons to travel through. Electrons move in the empty spaces within and between the atoms of a conductor. As each electron moves uniformly through a conductor, it pushes the one ahead of it. Thus, all the electrons move together as a group. When you unplug an appliance, say a toaster, from the power supply, the flow of electrons is interrupted and the appliance stops working. You can measure electric current as the rate of flow of charge, or the amount of charge flowing through a point per unit time. Electric current is measured using an ammeter. The standard metric unit for current is ampere. Ampere is often shortened to amp and is denoted by the unit symbol A. 1 ampere is equal to 1 coulomb of electric current per second. Electric current is a result of potential difference across 2 points in a conductor. Potential difference is the difference in number of negative charges that leads to flow of electrons. Electrons flow from negative potential, that is, the point with more electrons, to positive potential, that is, the point with less electrons. Whenever there is a potential difference, the current flows from the positive potential end to the negative potential end. Numerically, potential difference is the work done in moving a unit charge between 2 points in an electric field against the force of the electric field. Potential difference is measured using a voltmeter. Potential difference is often referred to as voltage and is represented by the letter V. If the work done to bring a charge of 1 coulomb from one point to another is 1 joule, then the potential difference between the points is 1 volt. As against potential difference, potential is the work done in bringing a unit charge from infinity to a point. Thus, if the work done to bring a unit charge from infinity to a point is 1 joule, then the potential at that point is 1 volt. In the given example, potential difference between points A and B is the difference in the work done in moving a unit charge from point A to B. Conductors can be in solid as well as liquid states. In solid conductors, positive ions are immobile and only the negatively charged electrons flow from high negative potential to positive potential. This flow of electrons is known as electric current. In liquid conductors, the current is caused by the flow of charged particles in both directions at the same time. In addition to potential difference, electric current is impacted by another factor called electric resistance. The electrons in a conductor do not travel in a straight path from one end to the other. While moving across the conductor, the electrons collide with fixed atoms within the conductor. encountering hindrance in their movement. This hindrance or opposition to the flow of electrons is called electric resistance. While the electric potential difference between two terminals encourages the movement of charge, resistance discourages it. Thus, the rate at which charge flows from terminal to terminal is the result of the combined effect of these two quantities. The standard metric unit of resistance is ohm, represented by the Greek letter omega. When 1 ampere current flows through a conductor across a potential difference of 1 volt, its resistance is 1 ohm. Resistance to charge flow within a conductor is affected by some clearly identifiable variables. First, the resistance of a conductor is directly proportional to its length. The longer the conductor, the more resistance it offers. After all, if resistance occurs as a result of collisions between electrons and the atoms of the conductor, then there are likely to be more collisions in a longer conductor. More collisions mean more resistance. This relationship between resistance and the length of the conductor is termed as the law of length. Secondly, the resistance of a conductor is inversely proportional to its cross-sectional area. Larger the area of the conductor, lesser the resistance offered. This relationship between resistance and the area of a conductor is termed as the law of area. The third factor that affects resistance to charge flow is the material that a wire is made of. Some materials are better conductors than others and offer less resistance to the flow of charge. For example, silver is the best conductor. However, silver is never used in wires of household circuits as it is expensive. Copper and aluminium are among the least expensive materials with suitable conducting ability to permit their use in wires of household circuits. The conducting ability of a material is often indicated by its resistivity. Resistivity of a material is the resistance offered by a conductor having unit length and unit area of cross-section. The resistivity of a material depends upon its electronic structure and its temperature. The fourth factor that impacts the resistance of a conductor is temperature. For most materials, resistivity increases with increasing temperature. The variables affecting resistance can be mathematically written as R is equal to rho L divided by A, where R is the resistance in ohm, rho is the resistivity in ohm meter, L is the length of the conductor in meter, and A is the cross-sectional area of the conductor in meter square. In 1827, a German scientist, George Simon Ohm, conducted a series of experiments to study the variations in electric current when the potential difference across a conductor was changed. With the findings of his experiments, he postulated Ohm's law, which explains the relationship between electric current, voltage, and resistance. Ohm's law states that electric current through a metal conductor in a circuit is directly proportional to the potential difference or voltage across it, and inversely proportional to the resistance between its ends. Thus, according to Ohm's law, voltage V is equal to the product of electric current I passing through the conductor and the resistance R offered by it. Let us use an example to see how these equations help us analyze simple circuits. In the given circuit, there is only one source of voltage, a battery with 12-volt EMF, and only one element of resistance to current, a lamp with a resistance of 3 ohm. Using Ohm's law, you get the voltage in the wire as 4 ampere. Ohm's law states that at a given constant temperature, current I through a conductor between 2 points is directly proportional to the potential difference or voltage V across the 2 points. Thus, the ratio V to I is constant and is called the resistance R of the conductor. Consider a circuit with a battery, a rheostat, a key, an ammeter and a resistance wire connected in series. A voltmeter is connected in parallel to the resistance. Care is taken that the positive terminals of the ammeter and the voltmeter are connected to the positive terminal of the battery. The key is closed and the rheostat is adjusted such that the ammeter and the voltmeter show the minimum reading. The rheostat is then adjusted gradually, and the readings in the voltmeter and the ammeter are recorded at different instances in a tabular form as shown. Let the current passing through the circuit at any given time be I ampere and the potential difference across the resistance be V volt. The ratio of potential difference V to current I gives the value of resistance R in ohm. You will observe that the resistance is almost constant for different pairs of VI values. If you plot the values of V against I on a graph with V on the y-axis and I on the x-axis, it will be a straight line as shown here. This verifies Ohm's law. This graph is known as a VI graph. The slope of a VI graph can be determined by taking 2 points P and Q on the straight line. From points P and Q, draw normal lines to the x and y axis. Point C is the foot of the normal line from P to the x-axis, and point A the foot of the normal line from point P to the y-axis. Point D is the foot of the normal line from point Q to the x-axis, and point B the foot of the normal line from point Q to the y-axis. Distance AB represents delta V, or change in potential difference, while distance CD represents delta I, or change in current. The ratio delta V to delta I, which is also the slope of the VI graph, gives the resistance R of the conductor. The higher the slope of the VI graph, the higher is the resistance of a given conductor. Let us now consider the VI graphs of a conductor at 2 different temperatures, T1 and T2, where T1 is greater than T2. Thus, T2 is the temperature of the conductor before it is heated, and T1 after it is heated. The VI graph of the conductor after it is heated is steeper than its VI graph before heating. This is because as the temperature rises, the resistance of the conductor increases. Conductors that obey Ohm's law are called ohmic conductors or linear resistors. For example, metals such as iron, silver, copper, etc. at constant temperature are ohmic conductors. For all ohmic conductors, the VI graph is a straight line, and the value of resistance R remains constant at a given temperature for any of the values of V or I. Conductors that do not obey Ohm's law are called non-ohmic conductors or non-linear resistors. Diodes and triodes are the best examples for non-ohmic conductors. For all non-ohmic conductors, the VI graph is a curve instead of a straight line. This indicates that resistance R of a non-ohmic conductor varies for different values of V or I values. To determine the resistance of a non-ohmic conductor at a particular value of V or I, draw a tangent at the desired point and find its slope. The resistance of a non-ohmic conductor is also known as dynamic resistance, since it varies for different values of V or I. Experimentally, it has been observed that the resistance of a conductor or wire depends on its length and area of cross-section. The resistance of a wire increases with an increase in its length, meaning that the resistance of a conductor is directly proportional to its length, L. Let this be equation 1. The resistance of a thick wire is less than that of a thin wire. The resistance of a conductor is inversely proportional to its cross-sectional area, A. Let this be equation 2. For a conductor of circular cross-section, the area of cross-section is equal to pi r square, where r is its radius. Hence, we can also write that the resistance of the conductor is inversely proportional to the square of its radius of cross-section. Combining equations 1 and 2, we get R is proportional to L by A. Replacing the proportionality symbol, we use a constant ρ, which represents the resistivity or specific resistance of the conductor. Now, we have R is equal to ρ L by A. Let this be equation 3. From equation 3, we get ρ is equal to RA by L. If the length of a wire is 1 meter and its cross-sectional area is 1 square meter, then the resistivity ρ of the wire becomes equal to its resistance. Hence, resistivity ρ of a material is the resistance of a wire of that material of unit length and unit cross-sectional area. If the length and area are measured in meter and resistance is measured in ohm, then we get the unit of resistivity as ohm meter. The resistivity of a material depends on its nature and the temperature of the conductor. It is independent of the shape and size of the conductor. It is a property of the material of the conductor and does not depend on the potential difference applied across the conductor or the current through it. A good conductor has less resistivity, whereas a bad conductor or insulator has high resistivity. The resistivity of semiconductors lies between that of conductors and insulators. The resistivity, and therefore the resistance of a metallic conductor increases with an increase in its temperature, whereas the resistivity of a semiconductor decreases with an increase in its temperature. It is observed that the resistance of some materials like tin and lead decreases tremendously with a decrease in temperature in the very low temperature range of the order of absolute zero. Substances under this condition are called superconductors. The resistance of a superconductor is nearly zero at very low temperatures. The table here shows the resistivity of some materials. Another important property of a material that determines its ability to conduct electric current is conductivity. Conductivity, represented by the symbol sigma, is the reciprocal of resistivity. That is, sigma is equal to 1 by rho or L by Ra. Conductivity is measured in per ohm meter or Siemens per meter. Since conductivity is the reciprocal of resistivity, its unit is the reciprocal of ohm meter, that is, per ohm meter. Consider a circuit with a bulb connected to a switch and a cell in series. Let the switch be open, which implies that the circuit is off. For the bulb to glow, there should be a current through the circuit, which is nothing but a flow of positive charges from the higher potential end to the lower potential end. The bulb has some electrical resistance, and hence, a potential difference exists across its ends. The flow of charges through the bulb can be studied by an analogy, the flow of water through a pipe. Consider two water tanks connected by a pipe of certain cross-section at their bottom. The level of water in the two tanks is different. Therefore, water flows through the pipe from the tank with the higher water level to the other, until the level in the two tanks becomes equal. The rate of flow of water through the pipe decreases as the difference between the water levels decreases. The flow ceases altogether once the water levels are equal. To maintain a constant rate of flow of water through the pipe, the difference in the water levels in the two tanks should be constant. This can be done by pumping water from the tank with the lower water level to the tank with the higher water level. Thus, energy is spent by the water pump in lifting water from one tank to the other. In this way, a constant pressure difference is maintained across the water pipe. Similarly, a constant electric potential difference is maintained across the bulb by an electric cell. It maintains a constant electric current through the bulb. The free electrons in a conductor not connected to an electric cell move in random directions. Now, when the switch is turned on, even though the motion of the electrons remains random, but on the whole, they move in a specific direction. They move from the negative terminal of the cell to its positive terminal through the external circuit. As electrons are negatively charged, their flow is equivalent to the flow of positive charges from the positive terminal of the cell to its negative terminal through the external circuit, which we call an electric current. Thus, we can say that a cell moves positive charges through the external circuit from its positive terminal, which is at a higher potential, to its negative terminal, which is at a lower potential. Thus, the positive charges move through the external circuit from a higher potential point to a lower potential point. Within the cell, they move from the lower potential negative terminal to the higher potential positive terminal. Just like the water pump that lifts water from the tank with the lower water level to the tank with a higher water level, an electric cell raises a positive charge from lower potential to higher potential using energy. The chemical energy stored in the cell is used for driving positive charges from the lower potential to the higher potential. No external work needs to be done to make water flow from a given higher level to a given lower level. But work has to be done by a water pump to drive it from the lower level to the higher level. This implies that it is the energy spent by the water pump in lifting water that makes water flow from the higher level to the lower level. In a similar manner, the amount of energy spent by a cell in driving positive charges from lower potential to higher potential within the cell is used to drive positive charges through the external circuit from its positive terminal to its negative terminal. The amount of energy required to drive a unit positive charge through the external circuit is called electromotive force, or EMF. The cell is called the seat of EMF. EMF depends on the material of the electrodes and the electrolyte used in the cell. It does not depend on the shape of the electrodes, the distance between the electrodes, and the amount of electrolyte in it. Also, the EMF of a cell does not depend on the amount of current drawn from it. If W is the amount of work done by a cell in driving positive test charge Q0 through an external circuit from its positive terminal to its negative terminal, then its EMF E is given by W by Q0. The unit of work is Joule and the unit of charge is Coulomb. Thus, the unit for EMF is Joule per Coulomb. 1 Joule per Coulomb is equal to 1 volt. Hence, the unit for EMF is volt. The energy supplied by a cell to a charge is used to overcome the electrical resistance in the external circuit, and the resistance offered by the cell itself to raise the charge from lower potential to higher potential. The resistance offered by the cell when a charge is brought from lower to higher potential within itself is called its internal resistance. For an ideal cell, the internal resistance is 0. If an ideal cell is not connected to an external circuit, that is, when no current is drawn from it, then the potential difference across its terminals is equal to its EMF. If the ideal cell is connected to an external circuit, that is, if the switch in the circuit is on, then the potential difference across the terminals of the cell is equal to that across the resistance in the external circuit. Now consider the case where the cell is not an ideal cell. Let the internal resistance of the cell be R. Then, a part of the cell's energy is consumed by a charge in transit in overcoming the internal resistance. Let W be the total energy supplied by the cell in driving test charge Q0 through the complete circuit. Let W' be the energy utilized by the charge in passing through the external circuit. And let W be the energy utilized by the charge in overcoming the internal resistance of the cell. Then, according to the law of conservation of energy, we have W is equal to W dash plus W. Let this be equation 1. Dividing both the sides of the expression by Q0, we get EMF E is equal to V plus V, where V is the potential drop across the resistance in the external circuit and V is the potential drop across the internal resistance of the cell. Let this be equation 2. The potential drop across the resistance is equal to the work done in carrying a unit positive charge through the external circuit. It is also called the terminal voltage of the cell. Thus, the terminal voltage of a cell is defined as the potential difference across its terminals when it is in a closed circuit. According to Ohm's law, V is equal to I into R, and V is equal to I into R. Let these be equations 3 and 4 respectively. Substituting equations 3 and 4 in equation 2 and simplifying, we get the expression for the internal resistance of a cell, R is equal to E minus IR by I. The same expression can be rewritten in different forms, as shown here. The internal resistance of a cell depends on various factors, such as area of the electrodes. The larger the surface area of the electrodes, the less is the internal resistance. Distance between the electrodes. The more the distance between the electrodes, the greater is the internal resistance. Nature and concentration of the electrolyte. The higher the concentration of the electrolyte, the greater is the internal resistance. Temperature of the electrolyte. The higher the temperature of the electrolyte, the less is the internal resistance.